These pictures show a sequence of a balloon filled with hydrogen igniting from a flame. The rubber of the balloon quickly disintegrates, and a ball of flame is shown as tremendous amounts of energy are released as the hydrogen bonds to the oxygen to form water. We represent what happens in a balanced chemical equation. 2H2 plus O2 yields 2H2O. Another way to represent this is as a series of pictures representing the actual molecules. Here's H2, here's another H2. That's 2H2. Here's one molecule of oxygen. So what happens is this hydrogen molecule breaks apart into two hydrogen atoms. So does this one. And the oxygen molecule breaks apart into two oxygen atoms. And then the atoms recombine to form water, or H2O. So this represents two molecules of hydrogen reacting with one molecule of oxygen to form two molecules of water. Well, if that's true, would it also be true that 2,000 molecules of hydrogen react with 1,000 molecules of oxygen to form 2,000 molecules of water? Well, sure it would. It would still represent a ratio of the molecules rearranging their atoms to form water. Only we're scaling it up to 2,000 molecules of hydrogen and 1,000 molecules of oxygen. How about 2 trillion molecules of hydrogen reacting with 1 trillion molecules of oxygen to form 2 trillion molecules of water? Yes, again. How about if 2 grams of hydrogen react with 1 gram of oxygen to form 2 grams of water? Can we say that? Does this picture support that? The answer to that is an emphatic no. This picture doesn't really show anything about the mass of these. It talks about the number of particles of them, but not the mass of them. While we can calculate a mass relationship between hydrogen and oxygen from this information, it will not be a 2-to-1 mass relationship. It is instead only a 2-to-1 relationship involving the number of particles reacting. The hydrogen molecule has a mass of 2. The oxygen molecule has a mass of 32. So that's 4 grams of hydrogen reacting with 32 grams of oxygen. A 4 to 32, or a 1 to 8 mass relationship. It's not a 2-to-1 hydrogen to oxygen particle relationship. Could we say that 2 moles of hydrogen react with 1 mole of oxygen to form 2 moles of water? Well, absolutely, because moles is just another particle relationship. It is a large number of particles, but it's still a numbers relationship. 1 mole is 6.022 times 10 to the 23rd particles, or molecules. So the balanced equation not only tells us what's happening on a molecule level, but it also tells us what happens if we scale it up to a mole relationship. It's still going to be 2 to 1 to 2. Only in this case, with moles, it'll be 2 moles of hydrogen react with 1 mole of oxygen to form 2 moles of water. Now, what would happen if we had 3 molecules of hydrogen and 1 molecule of oxygen? Would they be able to react together to form a product? It's a 2 to 1 to 2 relationship, and we'd still end up with 2 molecules of water, and the odd molecule of hydrogen, the third molecule of hydrogen, is not going to be able to react. It's going to be in excess, and it's going to carry over to the product. It'll just be floating around in excess. So now we want to start talking about how to use these balanced equations to solve problems, chemistry problems. Here's one. If you start with 6.2 moles of potassium chlorate, KClO3, how many moles of oxygen are produced? The balanced equation tells us that for every 2 moles of KClO3, we get 2 moles of KCl and 3 moles of O2. That's what it tells us. So therefore, this provides a relationship that we have a ratio of 2 moles of KClO3 for every 3 moles of O2 produced. So what we can do here is to use this mole relationship and apply it to the given number of moles, 6.2 moles of KClO3. And we multiply it by this relationship, by this ratio of 2 KClO3 to 3 O2. We're careful to put the KClO3 in the denominator because we want it to cancel out. So we put 2 mole of KClO3. This from the balanced equation forms 3 mole of O2, again from the balanced equation. So when we multiply that out, we get 9.3 moles of O2. So this is an example of using the balanced equation and the mole relationship in the balanced equation to solve a chemistry problem from taking a given number of moles and calculating a target number of moles. For the reaction, methane plus 2O2 yields carbon dioxide and water, what we balanced before. How many moles of water will form when 1.5 moles of methane are reacted or burned in an excess of oxygen? So we're going to do exactly the same thing with this. Use our mole relationship. This time we're interested in the relationship between methane and water. And we're told that we have an excess of oxygen, so we don't need to worry about the oxygen. We have all we need and more. So how do we calculate the moles of water? We take our 1.5 moles of methane that are given. We apply the ratio 2 moles of H2O to 1 mole of methane to the given number of moles. And we end up with 3 moles of water are going to be formed as a result of this reaction. How many grams of water will form when 22.3 grams of methane are reacted or burned in an excess of oxygen? Okay, so now we have a different story. We're out of the realm of moles. We're on the level of grams right now. And remember, the balanced equation only is a mole relationship. It is not a gram relationship. So if we have to calculate grams of water from grams of methane, what we have to do is convert the grams into moles of methane, use the balanced equation to go from moles of methane to moles of water, and then convert the moles of water to grams of water. So it's going to look like this. First, we take our 22.3 grams of methane. There are 16 grams of methane per mole of methane. We're dividing by the 16 grams of methane, so grams of methane cancel out, and we're left with moles of methane. And just an aside here, do you see how careful I'm being to label my units here, so that I don't end up doing something stupid like putting 16 grams on top and 1 mole on the bottom. If I'm careful with my labels and make full, complete labels, I will guide myself to set up this ratio correctly. So it's very important for you to spend a little extra time to set up your ratios with full labels. So here we have moles, 1.394 moles of methane after I convert the grams to moles. Now, what was the next step? I'm going to have to take my moles of methane And now I can use the relationship in the balanced equation. For every 1 mole of methane, there's 2 moles of water. I can now use that relationship and apply it to the moles of methane to convert that into the moles of water. So 1.394 times 2 moles of water divided by 1 mole of methane. Again, methane on the denominator. So moles of methane cancel out. I'm left with moles of water. And finally, one last step, taking my moles of water and converting that to grams of water with its molar mass. So here's my moles of water, 18 grams of water per 1 mole of water. Multiply that out, moles of water cancels out, which gives 50.2 grams of water. Note that I'm rounding off at the very end. I'm not rounding this to 3 significant figures. I'm going to save my rounding till the very end to make sure that my significant figures match the significant figures embedded in the question itself. So just to recap, we take our given grams and use molar mass or atomic weight, whatever, to calculate given moles by converting grams to moles, then use the mole relationship in the balanced equation to get the target moles, then again using formula weight or molar mass to convert to target grams. Okay, let's do a little cooking now. Here's a recipe. 2 cups of flour, a half a cup of sugar, 3 eggs yields 1 cake. Don't try this at home. It's not going to give a very good cake. Okay, I'm just doing this for an example. But don't make a cake like this because it'll be awful. You're going to need a little water or milk in there. Anyway, so you rush to the cabinet, the pantry, and you see you have 5 pounds of flour, 2 pounds of sugar, 2 dozen eggs. Here's a little relationship. 4 cups of sugar or flour yields 1 pound of sugar or flour. How many cakes can you bake? What is the limiting ingredient? Well, you notice that your recipe is in cups of flour, but in the pantry you've got pounds of flour and pounds of sugar. You've also got 3 eggs in the recipe, but you know you have 2 dozen eggs in the fridge. So the first thing you're going to need to do is to convert your 5 pounds of flour into cups of flour. How many total cups of flour do you have? How many total cups of sugar do you have? And how many total eggs do you have before you can use the recipe? The recipe is in cups and eggs, not pounds. You can't use this recipe directly. You have to convert your pounds of flour and sugar to cups before you can use the recipe. You getting a little goosebumpy here? Do you see? Well, okay. Just wait. It gets better. Okay. So we're going to convert our pounds of flour. The directions told us that we assume 4 cups of sugar or flour per pound. So if we have 5 pounds of flour, and the relationship is that there are 4 cups of flour per pound of flour, that's given right in the instructions, then, you know, we've got 20 cups of flour to work with. Yeah? And what about sugar? Well, same kind of thing. I've got 2 pounds of sugar. It's 4 cups of sugar per pound. That means I have 8 cups of sugar in the pantry. And as for the eggs, I have 2 dozen eggs. We know that 1 dozen eggs is 12 eggs, so I have 24 eggs in the refrigerator. So what do? Restating this question, I'm now stating it in terms of the amount of cups of flour and sugar and eggs that I have to match the recipe. So now we're ready to start actually figuring this out. How would you do this? Could you do this? Why don't you turn off the playback or the video and just work this calculation out. How many cakes can you bake? That's what I'm asking. And then come back to the video. Okay, so here we go. Let's see if you got this. What I'm going to do is find out how many cakes I could bake based on each ingredient. For example, if I have 20 cups of flour in the pantry, and I know from the recipe that 2 cups of flour yield 1 cake, I apply that relationship to the 20 cups of flour, I know I can make 10 cakes from the flour if the other ingredients were sufficient. I could, based on just the flour, I could bake 10 cakes. The sugar, I could even bake more cakes. I have 8 cups of sugar, but it's only a half a cup per cake from the recipe. If I apply that to the 8 cups of sugar, I can bake 16 cakes. I also have the 2 dozen eggs, 24 eggs, and 1 cake requires 3 eggs, and I can only make 8 cakes based on the eggs. So there it is. The eggs are what we call the limiting ingredient. The eggs determine how many cakes I can bake. The flour and the sugar are all going to be in excess. There's going to be flour left over. There's going to be sugar left over. I'll use up all the eggs and make 8 cakes. So the next kind of question is, how much flour and sugar are left over? Well, how would we do that? We take our 24 eggs that I know I'm going to use, because that's the limiting ingredient. And from the recipe, I can see that 3 eggs react with 2 cups of flour. For every 3 eggs I use, I require 2 cups of flour. So I'm going to apply that recipe in the form of a ratio to the eggs. And if I multiply 24 by 2/3, I get 16 cups of flour will actually be used. But I have 20 cups of flour in the pantry. I'm going to use 16 of them. So I'll have 4 cups of flour left over. Now, see if you can do that with the sugar. How much sugar is going to be left over? Pause your video, do it, and come back. Okay, here we go with the sugar. I do the same thing. 24 eggs. I'm going to use up all the eggs. But the relationship between sugar and eggs is, from the balanced recipe, 0.5 cups of sugar reacts with 3 eggs. So 0.5 cups of sugar per 3 eggs, and that is going to give me 4 cups of sugar used, just like the flour. I have 8 cups of sugar in the pantry. I use 4 of them, so I have 4 cups of sugar left over. So the limiting ingredient not only tells me how many cakes I can bake, the limiting ingredient also tells me how much of the other ingredients are going to be used. So let's move on from our cake making analogy to an actual reaction. 2 moles of hydrogen react with 1 mole of oxygen to form 2 moles of water. And suppose we have 5 grams of hydrogen mixed with 8 grams of oxygen. What's the reagent in excess and by how much? So in the cake making analogy, what we did is to find which ingredient gave the fewest cakes, and that was the limiting reagent. And the limiting reagent determines how much of the other reagents are actually used, and from that information you can find the reagent in excess and by how much. So what we have to do here is to convert each one of these reagents, 5 grams of hydrogen, 8 grams of oxygen, into moles. So of course for hydrogen we have 5 grams of hydrogen, and the relationship is that for every 1 mole of hydrogen it weighs 2 grams. We know that from the formula weight. That's the definition of formula weight. Grams per mole. Only this time we're putting grams in the denominator and moles in the numerator. It's the same ratio but inverted from grams to moles to grams. The reason we invert it is so grams will cancel out and we're left with moles of hydrogen. Now, the relationship between hydrogen and water is a 2 to 2 mole relationship. 2 moles of hydrogen from the balanced equation yield 2 moles of water. So we convert the moles of hydrogen into moles of water with that 2 to 2 mole relationship. Therefore, based on the hydrogen, we will have 2.5 moles of water forming. Okay, now what about the oxygen? Okay, for the oxygen we have 8 grams of oxygen. The molar mass is 32 grams per mole. We invert that so grams of oxygen will cancel out, leave us with moles. And then we use the 2 to 1 relationship. 1 mole of oxygen from the balanced equation yields 2 moles of water. It's a 1 to 2 mole relationship. And we make a ratio with that relationship, putting moles of oxygen in the denominator, so it will cancel with moles of oxygen in the numerator here. So we'll be left with moles of water in the numerator. So when we multiply all this out, 8 times 2 divided by 32, we'll end up with 0.5 moles of water as the amount of water formed on the basis of oxygen. So because the oxygen yields the least amount of product of water, it's the oxygen that's the limiting reagent. It limits the amount of product that forms, and it limits the amount of hydrogen that reacts. So in the next calculation, we start with the 8 grams of oxygen, we convert that to moles, and we use the relationship between oxygen and hydrogen, which is a 2 mole of hydrogen to 1 mole of oxygen relationship, to determine the amount of hydrogen that is actually going to react with the oxygen. So 8 times 2 divided by 32 is 0.5 moles of hydrogen. That's the amount of hydrogen that will be used. And converting that into grams, we just apply the molar mass to it. 0.5 moles of hydrogen times 2 grams of hydrogen per mole is 1 gram of hydrogen that's actually going to be used. Since we are starting with 5 grams of hydrogen and only 1 gram is going to be used, subtracting those gives us 4 grams of hydrogen that remains. So that is how much hydrogen remains after this reaction. Now when you actually run an experiment in the laboratory, you seldom get the yield that you calculate you should get. And usually that yield is smaller than the calculated amount, although sometimes it can be larger if you have, for example, impurities that haven't been removed. But the way you calculate the percent yield is to make a ratio of the actual amount you actually collect and divide that by the theoretical amount that you calculate you should get, times 100%. So that's what percent yield is. So for this question, we have a reaction, and if we start with 50 grams of cupric oxide and collect 25 grams of copper, calculate the percent yield. So the 25 grams of copper is the actual yield collected. That's what we actually collect. And the theoretical yield is what we have to calculate doing a regular stoichiometric determination. So we start with our 50 grams of cupric oxide. We convert that into moles. by dividing by the molar mass, 79.55 grams of cupric oxide per mole. We use the 2-to-2 mole relationship of cupric oxide to copper to convert from moles of cupric oxide to moles of copper. So we have 0.629 moles of copper, and that's the theoretical amount of copper in moles that we should get. If we multiply that by grams of copper per mole, the atomic weight of copper, then we end up with 39.9 grams of theoretical copper. This is what we would get if the reaction were to proceed with 100% yield. We didn't lose any in working it up. Everything worked exactly as it should, and this is the theoretical amount. But usually that's not the case. Usually we get less than this theoretical amount, and this question says we have 25 grams of actually collected copper, so we make up our ratio, 25 grams of actual copper divided by 39.9 grams of theoretical copper times 100. This is a 62.7% yield. Another kind of question you can get is kind of calculating from the other way around. You actually want to end up with 50 grams of copper, and the reaction proceeds with a 34% yield. So here you're being told what the percent yield is, and you have to calculate how much cupric oxide do you start with to take into account that 34% yield, so you actually end up with 50 grams of copper. So you do that, first of all, by taking this 34% yield and writing it as useful units. And percent means per 100. A 34% yield means 34 grams of copper actually collected divided by 100 grams of copper theoretically possible. And you see, we're going to try and calculate this theoretically possible amount of copper to use in our stoichiometric calculation. So we take our 50 grams of actual copper that we want, and we multiply that by the ratio inverted, so actual copper is in the denominator. And once again, here's the example of using full-fledged descriptive units and not taking shortcut with your units. If you don't make this a full unit, it's not just have 34 grams of copper, 100 grams of copper, but actually putting in actual, the word actual, and the word theory, you're going to have a tough time knowing whether you use it this way or put the 34 on top and 100 on the bottom and get the question wrong. Take the time to make full units. Can't stress that enough. So, if we do that, grams of actual copper cancel out. We're left with grams of theoretical copper, and it'll be 147 grams of theoretical copper. So now we'll calculate from the 147 grams of copper that are theoretically required, how many grams of cupric oxide will generate that. So we need to convert 147 grams of copper to moles of copper using the formula weight. I'm going to divide by the formula weight, 1 mole of copper per 63.55 grams of copper. Grams of copper cancel out. We're left with moles of copper, 2.31 moles of copper. Now we can use the stoichiometry in the balanced equation to go from moles of copper to moles of cupric oxide. It's a 2-to-2 or 1-to-1 mole relationship. So we apply that 2-to-2 mole relationship to the 2.31 moles of copper to get 2.31 moles of cupric oxide, and convert the moles of cupric oxide to grams of cupric oxide using the formula weight of cupric oxide, 79.55 grams of cupric oxide per mole. Moles will cancel out. We'll be left with grams of cupric oxide. Now we're going to show you a shortcut method for determining the limiting reagent. Here we have a reaction: calcium phosphide, Ca3P2, plus 6 moles of water yields 3 moles of calcium hydroxide and 2 moles of pH3, a compound called phosphine. And the question is, which reagent is limiting and what is the maximum weight of phosphine that can be prepared from 2 grams of calcium phosphide and 1 gram of water? So it's a classic limiting excess problem. And right now you know one method to determine that limiting reagent, the classic method. And you do that by determining which reagent gives the least of any one of the products. In other words, on the basis of the calcium phosphide, you might calculate the amount of calcium hydroxide or phosphine that forms. You do the same on the basis of the water, calculate how much phosphine is formed, and whichever one of these reagents gives the least of any one of the products, that is your limiting reagent. And that's the one that determines how much product forms. It's also the one that determines how much of the other reagent is consumed. So the limiting reagent is important to know. The shortcut method for determining the limiting reagent is kind of cool. You calculate the moles of each reagent, and then you divide its coefficient to get what we call comparison moles. So, for example, you would find how many moles you have of the calcium phosphide, and you would divide that by 1 because the coefficient is 1 here. In other words, it's fine as it is. For the water, you would again find the moles of water that you have, but you divide those moles by 6. Then you would compare those comparison moles, and the smallest of those identifies the limiting reagent. Then you go back and use the original moles of the limiting reagent as you normally would to calculate the amount of product or the amount of the other reagent that's going to be used. We have 2 grams of calcium phosphide. We find the number of moles of it by dividing by its formula weight, 182. We get 0.01099 moles of calcium phosphide. The coefficient in the balanced equation is 1. So therefore, the actual moles of calcium phosphide and the comparison moles are the same number. We're dividing by 1. 0.01099 moles of calcium phosphide is our comparison number. For the water, we do the same thing. We start with 1 gram of water. We divide by its formula weight. We get 0.0556 moles of H2O. But this we divide by 6 because the coefficient in front of water is 6. So the comparison moles is 0.0093. So that's a smaller number than 0.01099 if we compare the two comparison numbers. So therefore, water is limiting. Now, once we know the limiting reagent, we don't use the comparison moles any further. Don't get confused by the comparison moles. Once you figure out the limiting reagent, forget about the comparison moles, and you work with the original 0.0556 moles of water to do the next calculation, which is the standard calculation. Here's our original moles of water. We use the balanced equation to go from moles of water to moles of phosphine. It's a 2 to 6 relationship or 6 to 2 relationship. 6 moles of water goes in the denominator, so it'll cancel out. 2 moles of phosphine are in the numerator, So that gives us 0.0185 moles of phosphine. And converting that to grams, we multiply by the formula weight to get 0.63 grams of phosphine. And that is the maximum weight of phosphine that can be prepared, theoretically. So that's a new way and a shortcut way of calculating the limiting reagent. So here's a question that we're going to get in class. We're not going to do it in this lecture, but if you want to work on it, you'll be that much more prepared for lecture. 37.0 grams of phosphoric acid reacts with 6.84 grams of calcium metal, forms hydrogen gas and calcium phosphate. If 4.61 grams of calcium phosphate is collected, what is the percent yield? So this is a limiting excess problem. You are starting with an equation that's not balanced. You have to balance this equation first. Then you have to decide which is the limiting reagent, the phosphoric acid or the calcium metal. And you would do that by this, perhaps by this new shortcut method that I just taught you. And once you know that, you can calculate from that limiting reagent the amount of calcium phosphate that forms, and that will be the theoretical amount. The 4.61 is the actual amount of calcium phosphate collected, so now you can calculate the percent yield. So now we're going to consider a new concept called molarity, which deals with the concentration of a solute in a solution. There are three terms here when we make a solution. There's the solute, the solvent, and then the solution. When we take a substance and dissolve it in a solvent, the substance we dissolve is called the solute, and it's the substance in the minority. The solvent is the substance in the majority. Together, the solute plus the solvent form the solution. And molarity is a very important way of defining the concentration of that solution. Molarity is defined as the moles of the solute per liter of solution. So let's say we wanted to prepare a 1 molar aqueous solution of sodium chloride. The AQ means aqueous, and it means water is the solvent. So whenever you see AQ, you know immediately what the solvent is. It's water. 1 molar means you're dissolving 1 mole of sodium chloride in 1 liter of solution. Now, note the way this is phrased, 1 mole of solute per liter of solution. It is not 1 mole of solute per liter of solvent. And that really defines the way you have to go about preparing this solution. You cannot fill up your volumetric flask with water first and then add your sodium chloride, because that might change the total volume of the solution. And the definition is moles of solute per liter of solution. So you have to make it up this way. You take a little bit of water, maybe fill the volumetric a quarter or a halfway full. Then you put in your grams of sodium chloride or your 1 mole of sodium chloride and dissolve it. And then you continue adding water until you reach the 1 liter mark. Now you have 1 mole of solute per 1 liter of solution. You won't end up with 1 mole of solute per liter of solvent, because that's not the definition of molarity. So here's a question: how many moles of potassium carbonate are in 3.6 liters of a 1.8 molar solution of this salt? How would you go about this? You have 3.6 liters of potassium carbonate solution. The molarity is 1.8 moles of potassium carbonate per 1 liter of solution. We put 1 liter of solution in the denominator, so it cancels with liters of potassium carbonate, and we end up with 6.5 moles of potassium carbonate as the answer. There's another question: what volume of 0.22 molar barium hydroxide contains 3.12 grams of barium hydroxide? Now, our first step, obviously, since we're dealing with molarity, and that's moles of solute per liter of solution, and we're given grams, our first job is to convert grams to moles. So that's 3.12 grams divided by its formula weight. Grams cancels out, leaves us with moles of barium hydroxide. Now we can take those moles of barium hydroxide and take our molarity, which is 0.22 moles of barium hydroxide per liter of solution, but we invert that. And we invert it so moles of barium hydroxide is in the denominator to cancel out with moles of barium hydroxide that we have. And when we do that, we get 0.083 liters or 83 milliliters of barium hydroxide solution. So that's the volume of 0.22 molar barium hydroxide containing 3.12 grams of barium hydroxide. Now, stoichiometry problems, we've already seen how if we're given grams, we convert to moles, then we use the mole relationship in the balanced equation to take us to our target moles, and then back to grams. But this concept of molarity gives us yet another way to calculate moles. We might be given molarity and volume, because molarity times volume is moles. Then again, we use our mole relationship to calculate target moles. After we have target moles, we can calculate milliliters or molarity. The concept of molarity gives us yet another way of doing stoichiometry problems. 25 milliliters of 0.33 molar calcium nitrate is reacted with an excess of sodium phosphate. So here's the equation. Balance, then calculate how many grams of calcium phosphate are produced. Well, our first job is going to be to balance this equation here. So let's go ahead and do that right now. Let's see. We have, I don't know, phosphate. We have one phosphate over here and two phosphate over here. Why did I start on phosphate? I'm just totally arbitrary. You can start with calcium, you can start with nitrate, whatever. I'm choosing to start with phosphate, and I'm not balanced in phosphate. So I'm going to put a big 2 right here, and that gives me 2 phosphates, to balance 2 phosphates on the product side. Now I have 6 sodiums. 2 times 3 is 6 sodium. I only have 1 over here, so I'm going to put a nice big 6 right there. And now I have 6 sodium nitrate. And look, I need 3 calcium on the product side because it's Ca3PO4 taken twice. I only have 1 calcium. I think I'll put a 3 right here, and that'll give me 3 calcium on the reagent side to match 3 calcium on the product side. And it also gives us 6 nitrate on the reagent side to balance 6 nitrate on the product side. So here's our balanced equation. By trial and error, we have the same number of moles of calcium and nitrate and sodium and phosphate when we're all done on both sides of the equation. Now we can take the information given to us, 25 milliliters of 0.33 molar calcium nitrate, convert the molar into useful units of moles per liter, and that's 0.33 moles of calcium nitrate per liter of solution. I've converted my 25 milliliters into 0.025 liters of calcium nitrate, and I multiply the two. Liters will cancel out, and I'm left with 0.00825 moles of calcium nitrate. Now, remember, I'm trying to figure out the grams of calcium phosphate that are going to be produced. It's 0.00825 moles of calcium nitrate is what I'm starting with. Now I can use my balanced equation to go from moles of calcium nitrate to moles of calcium phosphate. So how do I do that? I use the 3-to-1 mole relationship. 3 moles of calcium nitrate form 1 mole of calcium phosphate in the balanced equation. So I make a ratio, putting calcium nitrate in the bottom, so it cancels with calcium nitrate. I'm left with 1 mole of calcium phosphate. That comes out to be 0.00275 moles of calcium phosphate. The question is asking for grams of calcium phosphate, so obviously I'm going to have to take my moles of calcium phosphate, multiply it by the formula weight of calcium phosphate, 310 grams per mole, to get 0.85 grams of calcium phosphate. So this is a problem in which you're given molarity instead of grams. You still have to calculate moles and use the balanced equation to go from moles of what you're given to moles of what you want, and then convert moles to grams in this case. So here's another reaction that you can expect in class. For the neutralization reaction, 3 moles of calcium hydroxide plus 1 mole of phosphoric acid yields 3 moles of water plus 1 mole of calcium phosphate. 58 milliliters of 6 molar potassium hydroxide react with 44 milliliters of phosphoric acid. What is the original molarity of the phosphoric acid before mixing? So we're going to do this one in class. Just a little hint, you're given the volume of the phosphoric acid. If you know the moles of phosphoric acid, you can pretty much figure out the original molarity of the phosphoric acid. So let's see if you can do this in class. You might want to work at it before you come to class, and then you'll be a whiz ahead of everybody. Okay, that's the lecture for part 1 of chapter 4.